Hello, everyone. Good morning. I hope you are well and welcome again to our channel. So, today we're going to talk a little bit about my PhD research topic, which is related to my to the job that I've been doing here. Okay. So, today I would like to talk to you about a new proposal for shear resistance in reinforced concrete beam column joints. Okay. This is just related to earthquake loading, as you can see from here. Okay, my name is Yuri, and today we're going to go through this journey. Okay, the outline of this research is pretty much separating these 6 topics. References are by the end. Okay, so a little bit about the context. So beam column joints, they are critical sections when we are considering the global behavior and local performance during earthquake loading when we are considering reinforced concrete performance. Okay, and why is that? Well, joints, they both resist the transfer load between beams and columns, and also they restrain the lateral deformation of columns, so they are very important. However, when these elements they fail, we have a brittle type of failure mechanism, which is very sudden and very it's very dangerous. Okay. Other characteristics about when this failure happens is that adjacent joints, actually adjacent elements, cannot reach their full strength. Okay, and because of that, structure might lose substantial amount of ductility, and also you can increase cyclic demands in specific elements, and we don't want that. Okay. Uh, about the academic situation, there is a huge debate on reinforced concrete joints because of this. All right. So the amount that we have on experimental campaigns, we see about a great deal of scatter when we see the provisions related to the shear strength of reinforced concrete beam column joints. Okay. And most of these equations, they lack experimental validation. So this is also a very important issue, okay? And due to some safety problems, these previous equations, they lacked some safety levels, and this is our main concern, okay? So my thesis is divided into the main goal and all goals related to it. The main goal pretty much is to develop a new formulation, okay? We want to predict shear resistance in beam column joints safely, accurately, and we need to have a proposal that is code friendly. This is very important. All the thesis goals, they are related to chapters on my work. So each chapter is going to be split, divided into 5 papers that we intend to publish. The first goal is to develop a state of the art that we have done it already. Second goal, which is chapter 3, we're going to compare design provisions from codes and robust experimental data. And we want to do that through the gathering of information to a database. Chapter 4, which is the third goal, is to develop a new formulation, and we are going to compare with codes, authors, and to the database to see how the values deviate. Chapter 5, we intend to enhance the provision accuracy through probabilistic techniques, and we also want to recommend design tables to be used in codes that can facilitate designers' work. And lastly, we want to develop also an American campaign in which we want to assess situations that are not included in previous experimental campaigns. All right. The structure of the thesis is right here, as you can see. So beginning the state of the art, we have to define pretty much what is a joint, okay? There is actually a very common mistake through terminology. A joint is actually a part of the connection, okay? So here, as you can see, we have the red square, which defines the joint boundary, okay? And we have the connection. The connection is not the part of it. The connection is all the elements, all right, combined into the joint. So we have the joint, the beams, and the columns. This is all the connection, okay? And speaking about connection geometry, we have pretty much internal joints and external joints. External joints might be divided in T and corner joints. The difference between those is that internal joints usually they have more axial load and lesser flexural moment. On the other hand, external joints they have lesser axial load and more flexural moment. Okay. In a 3D environment, we can see that we have many configurations from connections, and depending on the type of your joint, that can impact the behavior of the structure. We have actually the theoretical mechanisms that a building might fail. For example, when the building is capacity designed or when it's not. And we actually have mechanisms observed after post-earthquake events, in which we have different types of failures that we intend to speak. Okay. Here are some of the examples that we've seen in after earthquakes, ever since from 1960s until today. So here in all these pictures, we have specific earthquakes gathered from specific reconnaissance reports. Here, as you can see, we have examples of external joint fractures. We have examples of shear failure, actually shear bond failure. Another examples of failure that started in connections and they expanded into the joints. We have also joint fractures, excessive deformation, yielding from above columns penetrating into the joint. We have also shear fractures, bond split failure, and overall collapse. Some other examples here, we can see that lack of capacity designed, inadequate size of joints, inadequate confinement of the joints. We have also detailing provisions that are not good, wrong actually, in the anchorage, formation of plastic hinges into the joints, and utterly joint destruction. So these are very common types of failure that we have experienced, and we need to address this issue, okay, very quickly. In terms of capacity of the joint and demand, what we have pretty much, it's how we actually come up with the design provisions of beam column joints. Take this frame, for instance. This frame, when it's imposed lateral deformation due to earthquake loading, for example, stresses and forces are concentrated in the joints through deformation. If we get to this joint here, and we see that they are both actually happening, vertical loads and horizontal deformation happen on the joint and deformation of plastic hinges on beams. This situation we have at the boundary of the joint forces and internal moments that when we see them actually being loaded into the joint, we have a combination of forces that they surge into the boundary of the joint. The combination of these forces that come from the member's strength, we can actually assess the horizontal joint demand on the joint. Okay, so here we have the horizontal demands, and this is what we can use as a design. Okay, the horizontal joint demand is pretty much related to the plastic formation of strength on the adjacent members and the column shear load. Okay, once we know these variables, we can determine all the internal forces in the joint. Okay, so knowing that, how can these forces act on the joint, and what are the shear resistance mechanisms that they exist in the joint? So when you have these nodal forces, okay, coming from the adjacent members, we have actually four types of resistance mechanisms. We have two direct shear resistance mechanisms, which are the concrete strut mechanism and the truss mechanism. And we also have indirect shear resistance mechanisms, which are the aggregate interlocking, which is pretty much the trend from the crack opening to slide into the surface of each other. And we also have the double action, which is this guy here. Okay. So these indirect shear resistant mechanisms, they actually are not counted in the full cyclic ray response because, well, aggregate interlock will fade away as soon as you have sliding. And double action we don't consider to be a main source of mechanism because we expect great cracking to occur before you have dual action. And the idea is that we don't have to go through that cracking, okay? So we actually take these guys out of design. So coming back to the direct strength mechanism, the concrete strut mechanism is actually a concrete volume inside the joint that is under compression and is self-equilibrated with the nodal joints and is completely related to the strength of the concrete strut. Okay. We don't necessarily have to have reinforcements to this mechanism to work, but whenever you have confinement reinforcement, that actually helps the strut. It's a topic that we're going to brief talk about it soon. And about the truss, the truss mechanism, whenever you have the shear acting on the joint, you will have the transformation, the absorption of these stresses and strains into the joint core. This is made through the ties, which are horizontal and vertical reinforcements, that they are going to connect the boundary of the joint and they will permit the existence of smaller struts that they will uphold these loads. Okay, so we have these two interaction mechanisms that they will actually vary throughout the performance of the joint whenever you have cyclic loading. Okay, so in essence, we want joints to remain elastic, but whenever you have cyclic loading, these mechanisms and their strengths remarkably vary. Okay, due to pretty much cyclic deterioration of concrete or the steel rebars. Okay. And these steel rebars, they are just like design of beams for shear. They are supposed to be connected so they can try to close the diagonal crack that will form whenever you have the failure of the joint. And here is the effect of the cyclic loading. So whenever you have the joint starting to go through an elastic cycle, the concrete from the strut actually starts to crack and its strength is decreasing. Whenever the joint core is cracking, there is a shift into the resistance to the hoop action, okay, governed by the truss action. So the strut action actually, whenever it's being under cyclic loading, there is a shift in the strength to the shear reinforcement. Okay, this is related to the boundary conditions and how much crack penetrates into the joint or not. And this strut, this is the most important thing, we are not sure how much force can this strut uphold given the uncertainty of the cyclic loading. Okay, so for example, we have here an example of the strut that has no actual load. And when the beam reinforcement starts to yield, whenever you have the formation of the plastic hinges, then you have cracking on the boundary of the joint. And what that does is pretty much thinner the strut. So you would have less strength taken by the strut. Okay. And this is when it happens to switch. Okay. Crack starts propagating and you have less strength of the concrete. Okay. So models that we have in literature, there is a great debate specifically because of this effect. This is why we have much inaccuracy in shear strength predictions. Okay. Speaking still about the failure of the joint, we have actually three main stages that are very easily seen throughout the performance of the joints. You have a initial state called the stage one, where you have the joint working pretty much under elastic conditions. Okay, this is because the concrete strut has not yet cracked. Okay, So the stress within the strut is not greater than the diagonal crack strength, okay? Until you reach that point. Once you reach that point, the joint is expanding, okay, due to Poisson effect, and the lateral expansion it's provoking cracks. Okay, so you experience the swift between what you have the beginning of the crack and the beginning of the action from the hoops. Okay, and here we have to compare joints that are reinforced, that they have both horizontal and vertical reinforcements, shear reinforcements within the joint, and unreinforced joints. When you have unreinforced joints, you don't have the confinement restraints from the hoops, so the joint just loses strength until you have a final stage here, which we're going to talk really soon. And the reinforced joint, on the other hand, whenever you have the expansion, you have confinement restraints until these reinforcements they yield. When the stresses are bigger than the stress resisted by the hoops, they tend to yield. And when they are yielding, you lose both resistance from the strut and truss. And then you progressively lose confinement, and then you have softening decay. Okay. This strength decay goes all the way until what we call a residual strength. This residual strength is pretty much related to the double action that we talked previously. Okay. So stage 2 is between the first diagonal crack until hoops yield, and stage 3 is pretty much related to the progressive loss of strength. Okay. And we can clearly see this through his theoretical behavior. During the cyclic, we see the forces and displacements, and then we can track whenever you have this capacity drop. Okay, and this is related to many things, not only strength of materials, but adjacent members, connection, detailing, and etc., which are things that we're going to talk really soon. These are the cracking patterns that we have seen in laboratory compared to the post events, and we see major development of cracks within the joint when you have problems related to the effectiveness of this horizontal and vertical reinforcements. Okay, so there has been a lot of studies in the last 65 years in which we want joints to literally remain elastic. We don't want this. We don't want diagonal cracking to happen in the joint. We want failure to be extended to the beams actually far away from the border of the joint. This is a way we can remain the joint elastic. And these are the possible cracking patterns that initiate the failure mechanism, which they have been gathered and separated. We have, for example, formation of plastic hinges on the beams, remaining the joint elastic, until we have absolutely plastic formation from columns into the joints, and you have extension damage into these parts. We also categorized and access the formation of the joint because we think that is also an ultimate limit stage, not necessarily um, just a service limit state, because it will impact the overall response of the building that actually can create an eventual collapse. So speaking a little bit about the pioneering research, I'll tend to be fast here, but we are characterizing each period of 10 years, ever since it's first started in the 60s. Okay, so one of the first experiments that we saw from Hansen and Corner, they evaluated the hoop action and the advantage of the confinement, especially from joints and beams. After we have Corlett and Hansen, they have checked what we call the steel overstrength effect, which they impact demands on the joint, and they actually checked the possible reduction of confinement when you have confinement from the beams. Megan and Park, they also helped develop the shear theory of joints, and they assessed many codes, and they checked that diagonal cracking really prevents shear mechanisms from fully forming. Townsend, he evaluated the negative impacts of axial tensioning in columns, and they are pretty much related to bond failure and intense concrete deterioration under cyclic loading. Rentham, he observed the high strain gradients in joints throughout the joint depth. He evaluated the Hoops ratios that might be insensitive depending on the effectiveness of the anchorage. They also observed that cracks form corner to corner instead of following a 45-degree angle. Patton observed that once hoops yield, there is a rapid deterioration of the joint. Also, being transversal stubs might help. Actually, just stubs, not transversal. Stubs might help preventing anchorage failure. Smith assessed the intense bond failure once cracking commences. Pork and Polly, they suggested removing concrete contribution from shear provisions, and they also observed that flexural capacities were not reached once shear of the joint would follow the government design. Magid, she observed the beneficial effects of transversal stubs and shifting failures from the joints to beams. Uzumeri, he captured the beneficial effects of high axial loads into bone strength. Blackley recommended reduction in time spacing in regards to the capacity reduction factors due to insufficient core confinement. Park and Thompson observed beneficial effects of beam pre-stresses and closed ties benefits. They also observed that horizontal reinforcement might be insufficient to prevent shear failure, and large flexural members covers might be detrimental when covers falls out when you're considering the flexural resistance of beams. Nielsen and Lobsey, they tested under monotonic conditions many joints, and they observed many detailing and lessing techniques, and they helped develop many of the design formulations of corner joints, which is really important until today. Fenwick and Ivan, they investigated bone plates into reducing bore slip and yielding penetration. Mainheint and Girsa, they also evaluated beam column joints to check limits on strength increase with quantity of hoops, sorry. They also checked for concrete strength is an important parameter, but not linearly related to the strength of the joints. And that also strength hierarchy nor column axial load will interfere much in their campaign. Blackley investigates the benefits of pre-stressed and haunted beams. They said that they saw that haunched beams are lesser beneficial than pre-stresses, but haunched beams can also promote shifting beam column joint failure to beams. Park and Kong, they saw beneficial effects of column intermediate bars, and inclusion of beam bottom and top stresses increased strength and ductility. Banking sale, they observed the detrimental effect of bidirectional loading, which is very important in related to failure dominated by bone slip. And also bidirectional load decrease the effectiveness of lateral confinement, which is very important. Zhu and Girsa also observed the design requirements of this relation, column depth through beam bar diameter. And Leon observed that anchorage length is very important in maintaining the ideal response of connections. The other periods, we are still under development because we are extracting all the data to assemble the database. These are some of the lessons that we have learned. So the beneficial lacings that we have seen in corner joints, the bond plates and their significance, the core expansion, the use of pre-stress, more related to the mid-depth joint, transverse stubs into the shifting, and how different arrangements of reinforcements can be beneficial or not. And this is what we see into the design codes. So we want joints to remain essentially elastic. We want hinges to be formed into beams. Joints must have, okay, they must have both horizontal and vertical reinforcements in order to maintain the shear resistance mechanisms. The connections of the members around the joint, they must be really well designed, or else the damage from these connected elements will go into the joint. Columns, vertical bars must be continued through the joint, and the same for beam bars. Whenever you have external joints, then these beam bars need to be adequately anchored in it. And these members must comply with design requirements. Okay. So moving to the last part of the state of the art, we have evaluated many design requirements and author shear design codes, shear design strengths, sorry. And what we see is actually a very difference in every code, every author shear equation. There is like tremendous differences, and most of these proposals, they were done with some sort of database or experimental campaign um, to be based on. We're not going to talk about it. We're just going to show that we we evaluated 12 proposals, many of which we have many parameters considered, and all proposals, they tend to be different from one another. As you can see, none of those proposals, they absolutely take into consideration all parameters, but many of them, they tend to be quite accurate. This example and this example, for example, with different amount of parameters, you know. So this is something that is very interesting to talk about. So the methodology is divided by chapter. Okay. First chapter, we are going to develop a state of the art. We have assessed 65 years of research. We have cataloged authors, and we have observed many failures in the recognized reports ever since the 60s. And what we're doing is gathering experimental evidence so we can assemble the database. Okay. Chapter 3 is design methods. We are going to compare 17 different codes. We are going to compare these codes with the experiments to see how these equations perform, and we want to assess deviations. Chapter 4, we are going to develop an alternative formulation based on many different models. We still want to see if we're going to use principal stresses or Schroeder-Tide techniques or other formulation that we might see that might be a good proposal. After we have come up with an alternative proposal, we want to compare the predictions of this formulation to the previous results. So we are going to want to compare the authors and codes. And maybe if we don't have enough data, we might use a neural network to increase the sample size. This is something that it's an idea and we think it might work. Chapter 5 is related to the risk assessment, and what we want to do is design the table for engineers. We want to do, after the proposal is done, we want to do a sensitivity analysis to see what variables are highly impact. And what we want to do is, with that amount of data, we want to recalibrate if there is a need and weight different variables in order to decrease scatter. Once we have that done, we're going to use this formulation to create a design table for engineers to help them designing joints in cyclic situation. And lastly, we have chapter 6, which is going to be an interesting chapter because most most formulations, they were based on previous knowledge. Okay, so the idea here on chapter 6 is actually create new types of models that haven't been seen in experimental campaigns, and we want to see the performance of these new structures under our proposal. So we want to do that. How we are going to do that? We are going to use some benchmarks to calibrate numerical models. Then we're going to create maybe 8, 10 models to check features that usually are lacking in the database, such as high eccentricities, bidirectional loading, different boundary conditions that we haven't seen. And we want to see if the codes and our formulations they can fit into this as well. And finally, depending on what we see, we're going to um, suggest some conditions and some requirements to be fulfilled in future revision of codes. These are the 17 international codes that we have assessed so far. It's quite challenging, and we have checked in depth about what are the descriptions and the recommendations all of many requirement designs related to the seismic design of beam column joints. And as you can see here, uh, many of the design codes, they talk at least, or they have adequate recommendations towards this. The proposed schedule, we are actually here in the first year, so we are almost in the end of the first year. After this, we intend to conclude the database so we can move on to the next chapters. The doctor schedule is supposed to be 3 years, which we hope to complete. Let's see how it goes. And the last part of this presentation is how we're doing the database assemble. So the main problem that we have seen in databases is that usually they have not sufficient number of variables. Most of the experiments, they tend to be very heterogeneous, and we have problems related to results and predictions. And most authors, they use database as large as 50 to 600 tests. So what we want to do is pretty much have a thorough control of the data. We want to reduce scatter as much as possible by organizing really well the data. So we want to assess many design parameters, and we want to group them into a way that we can see better how the data deviates from experimental results. And if there is insufficient data, as we said, we're going to create synthetic data. So the data base is divided into 3 steps. So initial search, then verification of this data, and finally the input of the data into the spreadsheet. All the data that we're collecting are related to the boundary conditions of the beam column joints, mechanical properties, loading conditions, test equipment, and etc. We have estimated that we have 16 direct variables, and we have 32 direct variables that we are collecting throughout these experiments. And how we are doing this is, well, we check the paper or the report or whatever technical document that there is, information. So we see the scheme of the testing setup, and we see the sizes of the equipment, the scale of it, when was it designed, other characteristics such as the type of reinforcements, loading conditions, eccentricities, presence of infills, the type of joint anchorage, if there's the presence of cold joints, type of slabs, types of columns, ellipses, vertical joints. Anyways, there are many variables that we're collecting. And for the detailing of the members, we're actually taking that into consideration. We're seeing the design detailings of beams, columns, spandrel beams, joints details, slab details. We're collecting all these into different parts of the spreadsheets, so we can have literally all the informations of the connection and the connecting members. Okay. Once all that is input, we go into the strength of the connections. So we are assessing whenever we can find data in tables, it's easier for us. Whenever we cannot find, we extract data from the historical curves that we see in the experiments. So we are actually taking connection strength, hysteretic behavior, and failure modes into consideration. It is a very extensive job. We intend to finish this really time soon. And these are some of the reference. If you're interested, you just can stop the video and check yourself. And I would like to thank my professors for being here today, and I hope you liked it. If you have any questions, just let me know in the comments, or you can send this to my email.